This video on the Cisco Virtual Switching System using Quad SUP SSO technology is presented to you by the ENG Training Group in collaboration with Mahesh Nagireddy, Technical Marketing Engineer with Cisco Systems. The objective of this video is to provide an overview of the virtual switching system Quad SUP SSO technology and how it enhances the traditional VSS to provide an increased application uptime and simplified network design. This video covers a basic introduction to the virtual switching system or VSS technology and then explains the Quad SUP SSO technology, followed by a demo showing the configuration specifics and further links and contacts to obtain more details about the Cisco VSS Quad SUP stateful switchover. This VOD is intended to target anyone willing to learn about the Cisco VSS Quad SUP SSO solution. This VOD can be shared externally to demo the VSS Quad SUP SSO features and setup. Let's get started with a brief introduction about VSS or Virtual Switching System. VSS is a network system virtualization technology that pools multiple Cisco Catalyst 6500 and 6800 series switches into one virtual switch, increasing operational efficiency, boosting non-stop communications, and scaling system bandwidth capacity to 4 terabytes per second. The VSS technology takes two physical chassis and creates an active standby control plane relationship across the two chassis while creating an active data plane. In other words, a single management entity and configuration file exists because of this active standby control plane. However, both chassis can forward data. This creates what appears in the network as a single device with 1+1 chassis redundancy. Because the VSS appears as a single logical entity, the network design itself is also simplified. With a single logical device instead of two, there is no longer a need to use first hop redundancy protocols such as hot standby router protocol. Because the VSS is a single logical entity instead of two, this reduces the number of layer 3 peering relationships and therefore lowers the processing cycles associated with the routing protocols. Similarly, IP multicast routing is simplified because there is no longer a need for two separate routers to negotiate a designated IP multicast forwarder. The VSS is made up of the following: virtual switch members, Cisco Catalyst 6500 and 6800 series switches, up to 2 switches with initial release deployed with a 10 gigabit Ethernet connection, a virtual switch link or VSL, 10 gigabit Ethernet connections, up to 8 using Ether channel between the virtual switch members. VSLs can carry regular data traffic in addition to the control plane communication between the two virtual switch members. The distance of VSL link is limited only by the chosen 10 gigabit Ethernet optics. A 10 or 40 gigabit Ethernet connection can be one or more of the modules shown here. The next concept to understand prior to an in-depth demo by our expert is that of Quad SUP SSO, or commonly referred to as VS40. What is Quad SUP SSO referring to? The VS40 technology enhances the VSS with support for redundant supervisor modules within a single chassis, referred to as in-chassis redundant supervisor module support. With VS40, the VSS is configured with 2 supervisor modules per chassis, thus the term Quad SUP or 4 supervisors. The second supervisor module within the chassis can be described as an in-chassis standby supervisor. With each local chassis, the 2 supervisor modules use stateful switchover technology to establish an SSO active and SSO standby hot control plane redundancy relationship. In the unlikely event that the active supervisor should fail, the standby hot supervisor will immediately transition to the active role. This transition occurs in a sub-second manner from the data plane forwarding perspective. In fact, the local chassis remains operational, keeping all links active. In this case, we can describe the redundancy relationship as 1-to-1 within the VSS chassis, followed by a 1+1 across the VSS chassis. SSO technology is essentially a group of Cisco iOS software processes that provide for supervisor module redundancy. In a standalone chassis, for example, the redundant supervisor module operates in a 1-to-1 active standby hot redundancy mode, providing redundancy for both the control plane and the data plane. The Cisco iOS software SSO processes build and maintain the redundancy relationship between the supervisor modules. The supervisor modules use a protocol to arbitrate which becomes the active and which becomes the standby hot. The active supervisor will provide the control plane functionality for the overall device, creating a single logical entity. The active supervisor synchronizes certain primary Cisco IOS software processes and data structures with the standby supervisor module. The active will continue to synchronize the primary information so that in the event of active supervisor should fail, the standby can assume the active role immediately. SSO technology later evolved to support the VSS, where supervisor engine redundancy is established across two chassis. The VSS uses dedicated physical link called the virtual switch link between the two chassis to synchronize the supervisor modules in each chassis. VS40 evolves the SSO technology yet again to support redundant supervisor modules within the physical chassis as well as across two chassis in a VSS. VS40 enables the supervisor modules to maintain two different redundancy relationships. One primary redundancy relationship, which is always across chassis and is maintained for the overall VSS, and a secondary redundancy relationship maintained within the local chassis. VS40 in effect provides 1+1 redundancy across two chassis and also 1-to-1 redundancy with the local chassis. Let's take a look at a brief demo by one of the subject matter experts, Mahesh Nagireddy, Technical Marketing Engineer with the Enterprise Networking Group.
As a part of this demonstration, I would like to give you an overview of virtual switching system, Quad SUP SSO technology, and how it enhances the traditional VSS to provide an increased application uptime and a simplified network designs. So what is VSS? Virtual switching system pools two Catalyst 6500 chassis into one virtual switch, providing single point of management, single configuration file, and a single control plane. So before we move on to Quad SUP SSO, let's review the traditional VSS architecture, which has one single supervisor per chassis, with which the switches can provide 1+1 chassis redundancy. In an unlikely event of a supervisor module failure, the local chassis is rendered non-operational with just 50% of the bandwidth available across the campus layers. Hence, with traditional VSS, we have undeterministic recovery time and a severe impact to any single homed devices. Hence, to overcome the above downsides, Catalyst 6500 switches running 15.11 SY with Supervisor 2T now supports in-chassis standby supervisor within the chassis along with stateful switchover technology. So hence, in an event of an active supervisor failure within the chassis, the standby supervisor can resume the active role with sub-second convergence. Quad SUP VSS uses multiple redundancy domains, the in-chassis redundancy domain within the chassis and the default redundancy domain across the chassis. So during a boot up process, the supervisor module with the lowest slot number becomes the in-chassis active and the other becomes the in-chassis standby. The in-chassis active communicates across the VSL, which are part of the default redundancy domain, and form VSS active and VSS standby from the overall VSS perspective. So hence, in the event of an VSS active supervisor failure, the VSS standby supervisor across the switch 2 resumes the VSS active role and the in-chassis standby SUP within the switch 1 resumes the in-chassis active role for that particular chassis. The switchover time for within and across the chassis is sub 200 milliseconds. The same procedure repeats for the next supervisor failure or the switchover. So the diagram on this slide depicts my current lab setup. Two 6807XL switches, which are part of my distribution layer with respective line cards installed, and I've got two 4500X switches which are part of my access and the core layer. I'm running an L2 port channel towards the access layer and an L3 port channel running OSPF between the distribution layer and the core layer. The traffic generator, which is generating bidirectional traffic across the setup. Here are my console connections to all four switches. The access switch as depicted is a 4500X running 3.5.2 iOS XE software, and the show module output from the first 6807 XL switch, which is hosted with two SUP 2T non-XL versions in slot number 3 and slot number 4. And also I've got a 4-port 40 gig module in slot number 2, which is currently configured to operate in 10 gig mode only. The show module output from the second standalone 6807 XL switch, which has a similar hardware as of the first 6807 XL switch and running a similar software version, which is 15.12 SY1. The standby supervisor of both the chassis will have console disabled. The core switch is similar to the access switch, which is 4500X switch running similar software, which is 3.5.2 iOS XE. So now let's proceed with the configurations on the standalone 6807 XL switch to convert both the switches into virtual switch. Here are the configurations which needs to be applied on both the switches, and in the interest of time I would copy paste the configurations on both the switches. Next, we need to execute a command on both the 6807 XL switches to convert from standalone mode to virtual mode using the command switch convert mode virtual. Execute the same command on switch 1 as well. As part of the initial boot up sequence, switches determine two key factors. The first one would be the VSS configurations, and the second one would be the in-chassis redundant supervisor installed within the same chassis. So this way the switch tries to bring up the VSL interfaces up first, and hence we always recommend to have the VSL interfaces on the supervisor, so that supervisor is the first module which would be brought up from the entire chassis perspective. In case the VSL links are part of a line card, supervisor needs to go wake up a line card and bring the interfaces up before it communicates across the chassis. So this switch is initialized as virtual switch active processor. If you look at the next switch, here it says initializing as virtual switch standby processor for the entire VSS. So let me pause this video until both the chassis boot up completely. The switches are now being converted to VSS. Now let's verify using few of the show commands. Firstly, the console will be active only on the active supervisor, which is currently the switch 1 in slot 3, and all other consoles will be disabled. Show switch virtual. This command displays the virtual switch domain number, the VSS active and the standby switches. So currently you're on switch 1, the SUP on slot 3, that's the one which is active, and the other switch which is currently in standby. Show switch virtual role. This command displays the VSS role, the switch priorities, and the status information of each switch which is part of the virtual switch. Show switch virtual redundancy. This command displays the VSS redundancy status and will always list the current active supervisor module first. The supervisor module which has the keyword switchover target is the VSS standby, and that's a supervisor which takes over during the event of active supervisor switchover or failure. Show switch virtual link. This command displays the virtual switch link information, and the detailed keyword will give you more detailed information of VSL. So these are the 4 VSL links which are cross-connected between the two chassis, and 10 gig 145 is currently chosen as the control link. Show switch virtual link port channel displays the information about the VSL port channel, the physical ports which are part of port channel 1 on switch 1 and the physical ports which are part of port channel 2 on switch 2. The configuration with respect to port channel and OSPFs are already in place, so let's verify them. So we've got an OSPF relationship between the VSS and the core switch. So let's check the reachability end to end. First, let me try to ping the loopback IP address of the core switch, which is 2.2.2.2 from the access switch. That's reachable. 1.1.1.1 is the IP address of the loopback interface of the VSS switch. I'm able to ping that as well from the access switch. Let's try reachability from the core. .10.10.10.2 is the VLAN 1 interface IP address on the access switch 1, which I'm able to reach, and the loopback of the VSS core, which I'm able to reach as well. .192.168.2.1 is the IP address configured on the core switch, the interface which connects to my traffic generator. The interface on the traffic generator has got an IP address 2.2.2.2, which I'm able to reach it from the access switch. Similarly, from the core switch, I'll try to ping the IP address of the interface to which my traffic generator is connected, which is 10.10.10.3, which I'm able to ping as well. To confirm it's a live traffic across VSS, let's initiate some pings from the access switch to the traffic generator interface IP connected to the core switch, and let's shut down the interface on the core switch connecting to the traffic generator. So before I do that, here is the graph from my traffic generator, which is set to run a continuous traffic between the interfaces connecting to the access switch, which is having an IP address 10.10.10.3, and the interface connecting to the core switch, which is having an IP address 192.168.2.1, and the traffic is currently routed across the VSS. Before I do that, here's a graph from the traffic generator, which is set to run continuous traffic between the interfaces, and the traffic is routed across the VSS. Initiate continuous pings from the access switch as well. So the pings running, let me go ahead and shut down the interface on the core switch. So with interface shut down, we can see the drop in traffic on the traffic generator as well as the pings. Interface resumed back. Traffic resumes as well. So this confirms it's a live traffic across the setup. So with the pings running, let's do a supervisor switchover, and prior to the switchover, let's check the VSS status. So switch 1 slot 3 is the active supervisor, and switch 2 slot 3 is the switchover target supervisor, and that's a supervisor which takes over when the switchover happens. So the command to initiate the switchover is redundancy for switchover. So once the command is executed, the switch 1 slot 3, the current active supervisor, reboots, and the control passed on to the VSS standby soup, which is switch 2 slot 3. So from traffic generator graph, there wasn't any disturbance for the traffic, and hence that confirms it's a sub-second convergence, which is less than 200 milliseconds. The same holds good for the ping as well. The shows its virtual redundancy command output confirms that switch 2 slot 3 is the current active supervisor, and the next switchover target is switch 1 slot 4. I hope this demonstration was informative. Thanks for watching.
For further information, please feel free to contact these subject matter experts. For additional information, please refer to some reference links provided here. Thank you for watching. We hope this demo was useful to understand the Cisco VSS Quad SUP SSO technology.